Section 22.21 Ligand Substitution. The valence electron count does not usually exceed 18 because that would likely place electrons in the antibonding orbitals, and this would destabilize the transition metal complex. For example, in this reaction mechanism, we use this entering ligand L to replace one of the 6 carbonyl ligands, and this mechanism is likely dissociatively activated. Why is that? Well, just imagine if this solvent molecule forms a new bond with chromium, then this chromium would be surrounded by 20 valence electrons. That means at least 2 valence electrons will have to occupy the high-energy antibonding orbitals. That would destabilize the complex. So now get back to the electron counting. A free chromium atom has a 4s2 3d4 electron configuration. But in a transition metal complex, the energy of the 4s orbital is bumped up. Therefore, we have actually 6 d electrons centered on this chromium, plus 12 sigma bonding electrons from the 6 carbonyl ligands. We have 18 electrons. Among these 18 electrons, 12 electrons occupy the sigma bonding orbital, 6 electrons occupying the pi bonding orbitals. Now if we have additional solvent molecule bonded to chromium, well, that will result in 20 valence electrons. Very likely, 2 electrons will occupy either pi star or sigma star antibonding orbital, and that's not stable. So again, this is the one of the reaction mechanisms that can be used to explain how this L ligand replaces a carbonyl ligand. So if you place this transition metal in a solvent, and very likely the solvent with a much higher concentration will replace one of the CO first, and then this entering ligand L will replace this solvent to form the final product. Finally, if you have bulky ligands, steric crowding may promote dissociative processes, because that's going to be more stable, and suppresses associative processes, because this is going to be less stable in a steric crowding environment.